Okay, so a very warm welcome to everybody, and thank you for joining Dr. Michel Wortmann, Dr. Kai Schröter, and Dr. Jelena Radonić, and myself, Brendan O'Flaherty, for today's webinar. So in today's webinar, we will explore using multi-hazard, multi-risk catastrophe models to assess the flood risk on the current and future climate change. And we will be using an example from the Danube River Basin. So, unfortunately, today's webinar is sadly the last of this year's Oasis Hub series, a series that has given our Oasis Hub members, new and established, a unique opportunity to learn, interact, and ask questions from a truly global panel of industry and academic experts. So before I formally introduce today's panel, it's important that I mention Horizon 2020, so whose funding allows Oasis Hub to create this wonderful and insightful webinar series for you, our community. So a big thank you to Horizon 2020 from all of us. So today I'm joined by Dr. Michel Wortmann, postdoctoral researcher at the Potsdam Institute for Climate Impact Research in Germany. Dr. Michel focuses on the impacts of climate change on the reoccurrence of catastrophic flooding. He has gained significant experience in hydrological modeling, and he received his PhD in hydrology from the University College London, and that was back in 2017. Our second panel today is Dr. Kai Schröter, who is a senior hydrologist at GFZ in Potsdam in Germany. Dr. Kai is a staff member of the German Research Center for Geosciences, the Natural Research Center for Earth Sciences. Research at the GFZ is on the geosphere within the highly complex system Earth, with its further subsystems, its interacting subcycles, and its wide network of cause and effect change. Our final guest is Dr. Jelena Radonić, who is the Associate Professor and Chair of the Environmental Engineering at the Faculty of Technical Science at the University of Novi Sad in Serbia. Dr. Jelena is the head of the Department of Environmental Engineering, and since 2015, Jelena has been an Associate Professor of Environmental Engineering in Research and Environmental Sciences with a PhD obtained in 2009. So, as I hand over control to our panel, I'd like to encourage the audience to ask questions via the Q&A area, and our expert panel will be pleased to answer your questions at the end of the presentation. So, over to you guys. There you go. So, should be to you.
Whoop. Oh. Wait a minute.
You have your video on.
Great. Yeah. There we go. I'm sharing.
Brilliant.
Oh, is this video still on?
Yeah, you can turn the video off.
I'm not sure how that works. There we go.
There you go.
Hi everyone.
Wonderful. We got you.
Well, then you know what I look like as well. And good to meet everyone, and I'm going to talk you a little bit through the first part of this presentation here. I have focused on the hazard modeling of the Future Danube model, and this is a little bit of an overview of the CAT model chain. This is a fairly classical CAT model setup with one exception, that it actually is driven by climate model simulations at the very top here. And the rest of it is basically a stochastic weather generator that was developed at Imperial College London. And then we have a hydrological model that was developed here at PIK, and a camouflage that's also been set up here at PIK. It's the hydraulic model that's driving the hazard footprints. And the rest of it is basically the probabilistic flood model that Kai will talk about in a minute. Apart from this, we also have a Pluvial flood model that we have set up for selected cities in the Danube Basin. And that's kind of the main setup. We've designed this entire model chain with the insurance sector in mind. And we had several meetings with them to give us feedback, and been able to validate it with them and test it. And the latest was just last week, and we're still sort of in contact with them and try to put the finishing touches now on the Oasis LMF implemented version of this model. So key to this entire thing is, and I think this is something that the insurance sector might not be quite familiar with, is that it's driven really by regional climate model scenarios. They are called Cordex EU, and they basically give us input from large global and regional climate models that will then drive our weather generator and the rest of the model chain. Seeing that we want to actually investigate the effects of climate change, we look at two climate scenarios, the RCP 4.5 and 8.5. And we tend to look at a reference period, which is now here defined as 1970 to 1999. And then we compare this reference period, or the output of the model, to the future periods. And here we actually have 3 future periods, while the first one is basically defined as the current climate. It's centered around 2020. And this is supposed to represent the current climate conditions in this catchment. But we also tend to look at longer term horizons, such as the medium term future 2020 to 2050, and the long term future 2070 to the end of the century. And this is kind of classical climate science projections of climate change in all sorts of parts of the world. And we have done this here in the Danube catchment, particularly looking at flooding, pluvial flooding as well as pluvial flooding. So I'm going to go into this now. I'm going to go into the fluvial flooding hazard modeling part. That's something that I've been intensively working on, and it's by far so the largest modeling component and the most computationally intensive part of the entire model chain, because it entails running both a catchment model that is simulating volumes of water in the river, and then when this volume of water is exceeding the channel capacity, it is flooded into the area, into the horizontal component of it. And there you have the hydraulic model running, which is also fairly intensive. But we have used a camera flood, which is kind of not as detailed as some of the other 2D models out there, but it's able to really produce many footprints for 10,000 years, as you have seen here. So we can run the entire model chain, or the meteorological event set that image is producing here with the entire hydrological and hydraulic model components. And that's really important because you then have a large flood event set that will then feed into the flood loss model. Mike flood, I'll talk about Mike flood in a bit, but I'll first go into the hydrological modeling here. So this is the model domain. It really covers the entire catchment, 800,000 square kilometers, about 17 countries, all of Romania, all of Hungary, all of Austria, large parts of southern Germany, and some parts of Czech Republic and Slovakia, Serbia and Bulgaria. Here are a few stats on those model components. The subbasins are hydrotopes, the sort of basic computational units of the model, and the subbasins represent stream segments that you can see here in blue. And the validation stations are where we basically validate our water volume, our hydrological model water volume in the river. And they are pretty much spread out over the entire catchment. Romania maybe not as detailed, and sort of the Balkans a bit less, but yeah, that gives us a fairly neat look into the match between historical discharge and our discharge that we have simulated with the model. And here's just one example of this, the 2006 flood season. You see that the red line, that's the simulated discharge here, matches the black dashed line fairly well in most cases. And that's kind of the key to understanding or making sure that the model is really in tune with the observations. Just a little snapshot of just one stream segment here. This is just north of Budapest. This basically gives us a peak discharge for all recurrence intervals. You see that here on the horizontal axis, and discharge here on the vertical axis. And those different colors actually refer to the medium-term future and the far future here. And what becomes immediately obvious is that this actually goes up. So in comparison to the blue reference period here, meaning that, you know, the 100-year flood will actually have a greater peak discharge in the future periods as it had in the reference period. You could also express this the same change in changes in recurrence interval, and that is basically a shift of the same peak discharge vertically to the left, and then it becomes basically the 100-year flood might become a 10-year flood or a 50-year flood. And this is what the next map shows you, basically the changes of the 100-year flood to the current future. And we reckon that the 100-year flood basically in large parts of the catchment will become a 10 to a 50-year flood. So the recurrence of the same peak discharge is much more frequent. And in some parts it's more moderate change, or in Czech Republic we actually have a bit of a decrease in probabilities here, but the overall picture really is larger probabilities, higher probabilities of the 100-year flood. And we can basically say this for each of those 13,000 stream segments that we have over the entire catchment. So once we have simulated those floods in terms of water volume, we can actually also distribute that in space with our hydrological model, hydraulic model. And here is an example of a flood footprint from southern Germany without levees or without flood defenses. And I've also got the same thing here with flood defenses. It's basically just taking a different assumption on the water capacity or the channel capacity of those rivers that you see here. So we have basically used this hydraulic model to produce 25-meter hazard maps for the entire Danube Basin with 4 10,000-year runs for each period. So the historical period will have 4 10,000-year runs, and the 3 future periods also have the same. And these hazard maps will become a mean of those 4 simulations, each taking the 100-year flood, obviously, or the 50-year flood, or the 10-year flood. This is really variable, and what's shown here on the right is basically just the 100-year flood for southern Germany. And we have got these obviously for all future periods. And this is kind of a summary of this for the entire catchment, disaggregated into the different countries that have significant flood-prone areas. And you can see basically that this 100-year flood zone will, increase in the future. So the changes on the vertical axis here are significant, 10 to 20% in the future, already 10% in the current period, and this is continued over the 21st century, basically. So this will become a fluvial flood event set, and that's implemented already in Oasis LMF. So you can actually take this away and implement it in your own model chain or wherever you are employing this. Here are a few stats, just like for each period we have about 500,000 events over the entire catchment. It's discretized into 10 centimeter intervals up to 15 meters resolution, 15 meters depth, sorry, and into 1.9 million error parallel IDs, which basically is the unique model units of this Oasis LMF implementation. Just a little look into the different data sets we have up here. On the Oasis Hub, there's a sample data set and basically advertising what we have, the entire model, including a couple of screenshots. But we have also got actually a dedicated test server up where you can run this entire model in the Oasis LMF implementation, including a nice browser UI that you can see here on the right. And there's also a test portfolio that you can compare it to yours, and that's something that we have used with the insurance sector to kind of validate the model with their output also of their internal models. And with this, I'll come to the Pluvial hazard modeling, which has so far only been implemented for Budapest and Novi Sad and Bratislava. And this was mainly done by the DTU in Denmark. This is again the model chain here. It's kind of feeding its results also into the GFZ flood loss model. And it has a 2D, it's a completely dynamic 2D model by Mike DHI, and it simulates really pluvial, so flash flooding on a 25-meter digital elevation model. And it's kind of using a conceptual representation of the drainage basin that makes it a lot more portable to other areas. So rather than always implement a full drainage system that's actually been observed or actually been implemented in a particular city, it's taking a conceptual approach, basically saying that maybe a 10 or a 2-year rain event is actually drained by the drainage system. Beyond that, it will lead to flooding. And this is all implemented now for Budapest in particular, where we have some nice results here. This looks, this is, for example, a 100-year or a 2 to 100-year event, neatly identifying the flood-prone areas for those flash flooding. And this is for the present climate here. I'll just show you a couple of results. Since some insurers have also indicated that this is really interesting to have this in all parts of the Danube Basin, so covering entire countries, we've also come up with like a conceptual approach to actually represent flash flooding in the entire catchment recently, also on the 25-meter DEM, and is basically taking the overland flow from the hydrological model that I've just described before, and is filling a detrended the detrended 25-meter DEM, and that leads to sort of similar areas as you have seen before, but not in the same level of detail. So what we're planning to do here is basically just have those detailed simulations for the large cities, and then the rest of the catchment we have a coarser representation of pluvial flooding. And with this, I will hand over to the pluvial flood side, to the fluvial loss modeling side of Kai Schröter. Kai, can you control the screen?
Hi, Kai.
Can you hear us, Kai?
Kai, if you're on mute, be able to hear you. Okay, I think I can do that for you. Yeah.
Yes. Hello.
There we go.
There we go. Perfect.
So now you
You're
can hear
on.
me. Okay.
Yep.
That must have interfered with the changing
That's
of
okay.
control. Okay, sorry for that. Welcome everybody also from my side. So I'm going to talk you through now the second part, which is focused on the flood loss modeling part. So we have arrived now the whole chain of models with which Michel has introduced to you, and I'm not talking about these probabilistic flood loss models that allow you to translate these information that you have in terms of inundation depth, inundation intensity into something that is an economic loss. And we do our model development based on empirical data. So this is a data set that we've been collecting here at GFZ together with University of Potsdam and German Reinsurance since the flood in 2002. And with this collection of data sets, we have quite a big number of loss cases from different residential buildings, different objects that have been affected by flooding. And with these data, we do some analysis regarding, okay, what are these relationships of these observations that we have together with the relative loss. From this, we identify these variables that are most important to explain the relative loss, either to residential buildings or also to commercial buildings. So these are different sets of models, and we have worked a lot in this direction. And in this project, we have been working on a modeling approach that is based on Bayesian networks. So Bayesian networks is a probabilistic approach that allows you to describe the structure of different variables, how they interact, and allows you to infer about the predictor variable, which is relative loss. So we have built these models on these micro scale data, so based on individual objects, but these data are not comprehensively available, so everywhere in the world or in Europe or in the Danube region. So therefore we provide also some additional data sets that allow to run these models also on another scale, which is then the mesoscale. And for this we have derived a number of proxy data that are available for the Danube region, but also for the rest of Europe. I will come to this a little bit later in more detail. Okay, so this is the family of models that we have been developing within this project and also within other projects. So we have one dedicated model for residential fluvial flood loss. We have one model for commercial fluvial flood loss. And we have another model for residential pluvial flood loss. This is a little bit a different modeling approach, but essentially it gives similar quality of results. So these models are all implemented in the Oasis Loss Modelling Framework. So similarly to what Michel has told you about the hazard part, these tools are readily available to be implemented in your workflows if you use the Oasis Loss Modelling Framework, and you can do the vulnerability modeling with these models. I will now focus on the residential fluvial flood loss model to explain you a little bit about the details of this model. I think there's not enough time to cover all the models in detail, but just to give you a little bit of flavor of what these models actually are able to do. So these models are multi-variable models. They use a number of different input variables to explain or to estimate this relative loss. We have a couple of descriptors that characterize the flooding intensity. Among them is water depth, return period, and inundation duration at a certain location. And we have some information that describes the characteristics of the property that is affected by flooding. And this includes information about the building area, then if there are any precautionary measures taken, and also the flood experience of the household. So these are some information that are not usually included in such models. So we are able to explain or to describe different damaging processes with these models a little bit more in detail than the usual models are doing that. How does a Bayesian network model work? So it's basically a joint probability distribution that we try to describe with this model. So it's the joint probability of all the variables that are included in this model They are connected according to the graphical structure that I've shown you. And if you want to do some inference about one of these variables, in this case, relative loss, you will obtain the probability of this relative loss given an observation of a parent node that's according to the structure of the network, in this case, for this little example, the water depth. And this then gives you an idea, okay, if I observe a certain value of this water depth, I will have a probability distribution, a conditional probability distribution of this relative loss, which then gives you an information about the expected loss ratio to the affected entity, as it is displayed with these distributions on the left-hand side. With the whole model, this is a little bit more complex, and it is a simplified schema here. So the different variables that you see here, the original model are much more detailed, but you see that these different variables are discretized into different classes, and that the probability distributions of the different nodes that you see depend on the according nodes that are giving their information to the different nodes according to the network structure. So we have implemented this model. You see a number of variables which might not sound very familiar to you, which you are not used to work with in your loss modeling or risk assessment activities. And we want to add this information to you, that you can use it by providing different alternative data sources. But you also should have in mind that these models find also their application outside the insurance industry. So we have model data sources from hydraulic model, as Michel has introduced in the first part. So we have information about the water depth, inundation duration, and if we are working on an historic event set, we might also use the return period. For these future scenarios, this might be a little bit more difficult to define these return periods. Then we have information about the building area. So this is building footprint information and also building location. This comes from Open Building Map, which is basically based on OpenStreetMap data. And then we have information about flood experience, which is going back to the last 25 years and takes information from the Dartmouth Flood Observatory catalog, which has some spatial information about where floods occurred in the history, and there we just simply count the numbers of flood in different regions, which then allows us to quantify the flood experience. And we have this information available for the whole of Europe. It is indicated here. We also have derived some asset values, so the damage potential basically for residential areas, which is based on the land use land cover information, the Korean land use land cover maps for the whole of Europe, where we have mapped these specific unit values of residential buildings throughout Europe. And we can use this to then quantify the economic value of the loss. This model has been applied in different case studies to validate whether it really does what we think it should be doing. We have been applying this to a catchment in Germany, the Mulde catchment, the Lech catchment in Austria, which is also in the Danube area, and one catchment in Italy, the Danube River, where we have some empirical observations of flood losses. And this is reported here. So we have the 3 different case studies. What you see is the distribution of the loss estimates produced by the model. The red bars are the observed values, and you see that the model fairly well covers the observations, at least in the interquartile range, that is between the 25th and 75th quantile of the distribution function. So there is, of course, not a perfect match, but with this probabilistic model, we are able to frame this uncertainty and to describe the observed losses quite or reasonably well. So this is some validation activity that we've been doing. Then I move forward to the implementation to the Oasis Loss Modelling Framework. So these vulnerability models are actually translated into these vulnerability CSV files, which are then converted into the vulnerability binary files as a pre-processing step in the Oasis LMF kernel. And with that, we can link it to the hazard simulations by providing these intensity bin dictionary information, and we can also then apply it to a number of items that come from some exposure data sets. So this is all available also in the test implementation that Michel has been mentioning. And we have applied this for testing purposes to a virtual test portfolio, which we have created for the residential sector in the Danube region. So what you see here, these red points on the map are basically a random sample of 10,000 virtual objects from the Danube region. So this is not really actual buildings, but these are locations where we know that there are residential buildings, and we have extracted from our database these points and have created this set of a portfolio that might be useful to compare our model outcomes with other models that are available on the market. So these asset values that are behind this portfolio are based on this green land use land cover information, and the total exposure of this test portfolios is about 460 million euros. To give you an impression of the location of these buildings in terms of flood-prone areas, so the bluish areas that you see now here in comparison to the previous slides, if I go back once again and forward once again, you see that these some of these buildings are actually within the flooded areas, but not all of them, which is, I think, also something that is reasonable. So we have run this through the Oasis LMF test setup, and we obtain these aggregate exceedance probability curves. This is just what we get from our whole model simulations for the reference period here in light blue, with an annual average loss of around 500,000 euros. And then also just to show you how this can be used for the other scenarios that we have been simulating with the hazard module. So what would be the loss for the current future scenario? So that's the actual period that we are in right now. And you see already that there's already some shift in the annual average loss in comparison to the reference. So this type of information can be extracted from this model. If you're interested in that, we have this user interface, and I've just added some screenshots to give you some impression about that. So you can ask to get access to this user interface, and there you will be able to access all these data that we have provided. You can select different scenario runs that have already been done, but you can also create your own analysis and test a little bit around. And this also gives you then the possibility to explore your results, to have some graphical information based on the results that are obtained. So this is something that should make it easier also for people who have not really the experience to work with the Oasis LMF on their own machines. They have the possibility to take some first looks into these, into the model setup via this user interface. Okay, so I would like to hand over to Jelena.
Wonderful. Thank you, Dr. Kai.
Thank you. Hello, everybody, and welcome to our webinar. I will present you the benefit of the Future Danube model in supporting the adaptation decision-making in the investment sector, using the example of the proposed wastewater treatment plant in Novi Sad, Serbia. And Novi Sad is the second largest city in Serbia and one of the only two cities along the Danube which does not have a wastewater treatment plant. The second one is the capital of Serbia, Belgrade. The wastewater treatment plant is one of the large investments in infrastructure planned in the region, and the pre-feasibility study for its development has been financed by the EU through the West Balkans Investment Framework. Our goal was to ensure climate resilience of the wastewater treatment plant. In other words, to ensure that capacity and technology of the plant are adapted to possible extreme events under current and future climate conditions. Some of the key objectives of the pre-feasibility study for wastewater treatment plant in Novi Sad were identification of possible locations for the plant, determination of basin area for primary water collectors and pumping facilities accommodating connection of existing sewage network to the plant wastewater treatment plant, and assessment of wastewater treatment options and recommendation of the preferred process option compliant with international and national urban wastewater treatment directives and legislation. I can't move the slide. Okay. Within the pre-feasibility study, 12 potential locations were identified as possible construction sites for the wastewater treatment plant, and 3 treatment options were proposed. Construction of a plant with primary and secondary treatment facilities, plant with primary, secondary, and tertiary treatment facilities, and plant with primary and secondary treatment and upgrading of the treatment plant at the second phase, adding tertiary treatment facilities. Pre-feasibility study has obtained positive review in January this year, and 1 plant and the location assessed at the least cost option for 400,000 population equivalents has been adopted, with the proof that upgrade up to 500,000 population equivalents is possible at the same location in the case of population growth in future. Considering treatment level, primary and secondary facilities, and upgrading of the plant at the second phase have been adopted. Process option will be conventional activated sludge and biological nutrient removal. The steps that have to be taken within climate vulnerability and risk assessment are determination of the project climate sensitivity to relevant climate-related hazards, identification of the project exposure to current and future hazards and at the location where the wastewater treatment plant will be implemented, and identification and prioritization of key risks. The project climate sensitivity was determined in relation to a range of climate variables and secondary effects, climate-related hazards. The treatment plant is considered to have high sensitivity to the increasing temperature that returns with extreme rainfall and can cause flash pluvial and fluvial floods, increasing the water level. The extent of the exposure of the project's planned location to current and future hazards was identified in 2 steps. Within the first one, the exposure to observed climate, including temperature data analysis, precipitation data analysis, droughts, etc., was assessed. Thanks to the Oasis framework, precipitation temperature and flood information was available for Novi Sad, where the project is classified as sensitive or exposed to a climate variable or hazard. Identification of the project exposure to future hazards was conducted in the second step. Within the second step, temperature extremes, precipitation, and river flooding were considered. The Future Danube Model stochastic meteorological event set was used to show the occurrence of years with extreme temperatures. Also, the Future Danube Model was used to assess the future extreme precipitation events leading to pluvial flooding, as well as the probabilities of flood events of the Danube River that runs through Novi Sad. Where a project is considered to have high or medium sensitivity to a particular climate variable of hazard, the vulnerability of the project's location should be assessed. Under current climate conditions and exposure of the plant, it is obviously that the location is vulnerable because it is lying low and it is right next to the Danube. further identification and prioritization of risks as a method for analyzing climate hazards and their impacts have provided information for decision making. In this case, the detailed risk assessment was focused on the forecast of the heavy rain events, the possible amount of water from precipitation, and the frequency and intensity of flood waves. As the increasing frequency of heavy rains showed growing possibility of every kind of flood, we came to the conclusion that the capacity of the wastewater treatment plant is the most vulnerable. Recommendation measures to the designing process include building appropriate adaptive capacity of the wastewater treatment plant that could operate in extreme low and extreme high water levels, implementing the flood defense measures taking into consideration the predicted pluvial flood possibilities caused by heavy rainfalls, cooperating with the authorities and water management sector within the field of climate change and necessary adaptation measures in general, and using alternative methods that reduce emission of greenhouse gases like carbon dioxide, methane, and nitrous oxide, and consumption of power. Okay.
Fantastic. Wow. Thank you. And thank you all.
Thank you.
Great. We have questions that the audience have asked for all three. So, Michel, if I could ask you, so a question has come through. The DTM resolution is 25 m. I presume that's meters. Isn't it too coarse for urban areas? How have you validated your results?
So I'm guessing this is referring to the pluvial flood loss model, or the pluvial loss model. We have basically come to sort of a good trade-off here. I mean, we tried it actually in Budapest with a 5 meter resolution model, and I'm just gonna go back to those slides here. We just have it. Here we go. And that basically led to a whole sort of other range of problems, basically bridges and obstructions of the waterways that are not actual obstructions on the ground. And that basically requires you to do a lot more detailed modeling. So if you go down to like a meter or 2 meter resolution. And to kind of go on this conceptual level, the 25 meter is kind of the best available in Europe, and we can actually port it also to other areas fairly easily. And that was kind of the aim of this, not to have the most detailed and street and building level information, but to have a model that's covering basically the entire domain, a city or something a little bit larger, and be able to port it to other areas. And talking about the fluvial flood, I mean, this is, in terms of fluvial flood models, 25 meter is actually fairly high resolution. Many other models even a little bit lower, maybe 100 meters or so. And that is also fairly accurate in kind of identifying flood prone areas. Maybe not to the point that each address is in the correct grid cell there, but it's fairly detailed already.
Okay, wonderful, thank you. I have another question, and this is open to all of our panelists. In the Oasis model, what does the indicator and how is it calculated? So maybe Kai, would you like to take that one up?
Yeah, I think this goes in my direction. Yes, this is referring to the vulnerability model. Michel, if you could go to slide number 25, as I don't have any control. Okay, great, thank you. So here we see again the structure of the model, and there you clearly see the variable precaution that is asked about. So precaution is actually a variable that we derive from the empirical data that we use to learn our models and to parameterize our models. It is an indicator variable, so it represents, in this case of model, a certain amount of precautionary measures that are taken by a certain property or household. So this can be a selection of different precautionary measures, like a little bit of dry proofing, or maybe wet proofing, or moving items in the first floor once a flood warning is there. So we don't differentiate for these different types of precautionary measures that are possible to take, but we just indicate whether the household or the property takes any of these measures, and then we count how much they take it. This is information that is usually available, not available in other regions. We have this information from our interview data sets, and this information is something that clearly changes the relative loss ratio of an affected object. Therefore, we have decided to include it in this model. We are aware that this information is not always available, but this is not a major problem for the model approach, because if you don't have an observation of a particular variable, the other variables, in this case, flood experience and building area, which are parent nodes of this precaution variable, are used to explain the relative loss. So they then condition the node precaution, and then this information flows further into the relative loss. So we don't have this information available within our pan-European data set, because there is simply no data source available that allows us to derive this information. But if this information is available, it can be included in the model. And if you think about adaptation planning scenarios, and you want to have an idea what will be the quantitative effect of increasing the level of precaution in certain areas, this is something that should give you an indication or a quantitative estimate of what you can expect in terms of loss reduction.
Okay, wonderful, wonderful. Dr. Jelena, there is a question for you.
Yes.
And it is, what are the next steps in implementation of the proposed measures?
Okay, thank you. I will try to answer this. So at the beginning of the next year, the third stakeholder workshop will be held in Novi Sad, aiming to present obtained results and recommendations for designing this wastewater treatment plant in Novi Sad. And the project team will offer to the stakeholders possible adaptation measures for the city flood protection in general and the Danube water management in Novi Sad. And also the promising news is that the development of the climate change risk assessment study for the feasibility study of the wastewater treatment plant in Novi Sad has been approved. So we hope that this will be done and that we will have better situation after this feasibility study and of course the construction of the plant.
Okay, wonderful, thank you. There are a few more questions, so let's try and get through them as quickly as we can. Dr. Michel, there is one that is, what is the general trend of flood risk with climate change in the Danube Basin?
I mean, so some of this I've already talked about earlier. It's basically, we see increased temperatures, I mean, across Europe actually, and that's generally leading to more precipitation as well. More warmer air can transport more humidity, so we actually see more intensive precipitation and also more locked in precipitation patterns that will then lead to periods of larger larger precipitation events, and that lead to fluvial flooding. So overall, we expect really more flooding to occur in the Danube Basin, although there are some pockets where this is actually not true. Czech Republic, I think, was something that was kind of sticking out there, and where we saw actually less flooding. But yeah, overall, the overall picture is more flooding in the years to come.
Okay, wonderful. Dr. Kai, how does your model approach differ from established vulnerability models?
Okay, thank you. Well, okay, that's quite a broad question, but I try to make it clear. As I mentioned already in the presentation, so what we do is actually implement a multivariable modeling approach. So this is taking into account more information than it's usually done by vulnerability models, which maybe differentiate for different building types, not really taking into consideration information like precautionary measures or flight experience or other socioeconomic information that differentiates the relative loss. We also have additional variables on the flooding intensity side. So not only water depth, but also inundation duration, for example, that clearly includes other damaging processes and other mechanisms that cause the damage to an object. Then secondly, the model is probabilistic. So we get directly from the model an uncertainty information that is derived from the empirical knowledge that we have about these damaging processes. So referring back to our empirical data set, from this we also derive the information about the uncertainty and represent this also in an uncertainty range and distribution of the relative loss. Then third, maybe our model is published. It is transparent and open, and everybody can see and check the assumptions and also look into different underlying data that are used to run this model, check the assumption. It is validated against empirical evidence. So this is something that I think differentiates this model quite substantially from other models that are in the market. And as I mentioned, in the case of precaution, it is also possible to obtain results without complete observations. So you don't need to have all the observations of all the variables that are in this model, but you are able to also infer about relative loss with a selection of these variables.
Cool, wonderful, thank you. And this has to be, unfortunately, the final question, and that's to Dr. Michel. Why are not more CAP models including the effect of climate change? Which I thought was a really interesting question.
Yes.
Oh.
In short, I mean, they are new to the insurance sector, I would say, and that's probably the main reason, and that's including results of climate models in the entire model chain. So often you need to actually pre-process those outputs, or first of all create them. I mean, they are available now in the public domain, actually quite a lot. There are probably some IP problems also that need to be overcome, but generally they then need to be pre-processed, and it's a fairly large data set. And yeah, in the insurance industry, it hasn't really come to a realization that this is really important in the future, and also in the current future already. So the changes that we have seen in comparison to the reference period are already quite significant. So we would really encourage other insurance companies to really look at the effects of climate change that have already happened in the reference period to the current future.
Okay, thank you. So everybody, sadly, this is our final webinar for 2019. So I suppose I'd like to take the opportunity to remind our audience, of course our panelists as well, about the importance of Oasis Hub, which is a unique and a very special global window to free and commercial environmental and catastrophe risk data, tools and services. So the Oasis Hub community, believe it or not, has over 1,500 global industrial professionals and academic members, providing them with a community and infrastructure that allows them to explore, discover, and connect with other organizations and fellow professionals, as we've done today and throughout the webinar series that we've had in October and November. So it's also important to highlight that when data services and tools that we spoke about today are purchased by Oasis Hub, everything is reinvested back into the running of the hub, our hub, ensuring we continue to prosper on behalf of your and our community. So membership is free. So please, if you haven't become a member as yet, please do so. Whilst also, please also encourage industry friends and colleagues to do the same. It matters a lot. And I suppose finally, not only would I like to thank Dr. Michel, Dr. Kai, and Dr. Jelena, I'd like to pass on my gratitude and thanks to all who have given up their valuable time throughout the webinar series to share their expertise, and of course, Tracy Irvine, who has to have most definitely a special mention, who is our hardworking and brilliant MD, and Leo Hussain, who makes the Oasis Hub glide as smoothly as it does. So thank you both. So today, of course, we will follow up with a recording, and we will follow up with the slides, and they will also have all the doctors' details as well as mine. So if you wanted to have any additional information, so please feel free to do so. So, thank you.
Thank you, Brandon.
Thanks, everyone.
Thank you. Everybody have a wonderful day.
Bye.
Bye.
Bye-bye.
Bye-bye.
Take care. Bye-bye. Bye-bye.
Bye-bye.